Hey cosmic curious cats, ever stare up at the night sky and find yourself lost in the sheer immensity of it all? That sparkling tapestry of distant galaxies, swirling nebulae, and silent, ancient starlight. Most of us do at some point, letting our minds wander to the biggest questions there are. But have you ever paused to wonder about something even more fundamental than the stars themselves? Something that had to exist before the first speck of stardust could even form. We're talking about the very building blocks of everything, the universe's first atoms. It's a question that reaches back to the absolute dawn of cosmic time, a mystery so profound it makes even the grandest supernovas seem simple by comparison. This isn't just about how the universe started with a bang, but how the raw ingredients for that bang and everything that came after it came into being. Picture a universe that was once nothing but pure, unadulterated energy. How did that energy congeal, coalesce, and transform into the distinct particles that would eventually bond to form the hydrogen and helium atoms crucial for igniting the first stars? It's a puzzle that has haunted the greatest minds in physics, cosmology, and philosophy for decades, inspiring a breathtaking array of ideas that push the boundaries of what we can even conceive. Today, we're not just scratching the surface, we're diving headfirst into an extraordinary journey, peeling back layers of scientific inquiry and imaginative speculation. We're going to venture beyond the familiar cosmic landscapes and into the realm of the truly unknown, where the rules of physics as we understand them might have been born alongside the particles themselves. Get ready to have your mind expanded, perhaps even a little blown, because we're about to explore 30 wild, wonderful, and sometimes wonderfully wacky theories about how those primordial particles, those universe's first atoms, actually popped into existence. From quantum fluctuations in an infinitely small void to the intricate dance of fundamental forces in the universe's infancy, each theory offers a unique lens through which to view the very genesis of matter. Some of these ideas are steeped in complex mathematics, others are born from philosophical leaps, and a few might even sound like something straight out of a science fiction novel. But what unites them all is humanity's insatiable drive to understand our origins, to piece together the cosmic story from its very first syllable. So, buckle up, because this is more than just a theoretical discussion. It's an exploration into the very edge of scientific imagination, a quest to uncover the secrets of the universe's original blueprint. This is the story of how everything we see, touch, and are truly began. Our journey begins, as it must, with the undisputed heavyweight champion of cosmic origin stories, the theory of Big Bang Nucleosynthesis. This isn't just a hypothesis, it's a meticulously constructed framework, rigorously tested and supported by overwhelming observational evidence. Imagine, for a moment, the universe not as the vast, cold expanse we know today, but as an incredibly hot, unimaginably dense cosmic soup, just moments after the Big Bang itself. We're talking about temperatures so extreme they dwarf anything we can recreate on Earth, reaching into the billions of degrees Kelvin. In this infernal furnace, the fundamental particles, quarks and leptons, were zipping around with incredible energy. But as the universe began to expand, it also began to cool ever so slightly, creating the perfect conditions for something truly extraordinary to happen. Around 1 second after the Big Bang, the universe had cooled enough for quarks to coalesce into protons and neutrons, the building blocks of atomic nuclei. Yet it was still far too hot for these particles to settle down and form stable atoms. However, between about 100 seconds and 20 minutes after the Big Bang, a critical window opened. The temperature had fallen to roughly 1 billion degrees Kelvin, a sweet spot where nuclear fusion could occur. Think of it like a cosmic pressure cooker, perfectly calibrated for creation. At this temperature, protons and neutrons, driven by the powerful, strong nuclear force, began to fuse together. This wasn't a random process, it was a highly specific sequence of reactions. First, a proton and a neutron would combine to form a nucleus of deuterium, a heavier isotope of hydrogen. Then, two deuterium nuclei might fuse to create helium-4, the most stable form of helium. Some of these reactions also produced trace amounts of helium-3 and lithium-7. The beauty of Big Bang nucleosynthesis lies in its precise predictions. The theory doesn't just say hydrogen and helium formed, it predicts their exact cosmic abundances, and here's where the observational evidence truly shines. When astronomers measure the amount of hydrogen and helium in the oldest, most pristine parts of the universe, regions untouched by stellar evolution, they find nearly perfect agreement with these predictions. We observe the universe to be roughly 75% hydrogen and 25% helium by mass, with tiny fractions of lithium. This remarkable match between theory and observation is one of the strongest pillars supporting the Big Bang model as a whole. It tells us that the early universe was indeed a place where these light elements were forged in a fleeting, fiery ballet of particles. This crucial 20-minute window was enough time for these fundamental building blocks to form, but not enough time for the universe to cool further and allow for the creation of heavier elements like carbon or oxygen. Those would have to wait billions of years, patiently biding their time until the first stars ignited, providing the next generation of cosmic foundries. Yet, while Big Bang nucleosynthesis explains the birth of hydrogen and helium with incredible precision, it leaves a tantalizing question unanswered: what about everything else? What about the carbon in our bodies, the oxygen we breathe, the iron in our blood, or the gold in our jewelry? These heavier elements, as we just mentioned, are typically forged much later inside the fiery hearts of stars. But what if there was another, far stranger, cosmic oven at play in the very early universe, one capable of producing not just the familiar light elements, but perhaps even traces of heavier atomic nuclei? This brings us to our second mind-bending theory: primordial black holes as atom factories. Now, this is where things get truly wild, venturing beyond the well-trodden path of established cosmology into the realm of speculative, yet scientifically fascinating ideas. Imagine, if you will, the early universe not as a perfectly uniform soup, but as a place filled with extreme density fluctuations. In some incredibly tiny pockets, the density might have been so immense that gravity overwhelmed all other forces, causing these regions to collapse directly into miniature black holes. These aren't the supermassive behemoths we see at the centers of galaxies today, or even the stellar mass black holes born from dying stars. No, we're talking about primordial black holes, theorized to have formed just fractions of a second after the Big Bang, long before stars or galaxies even existed. Their sizes could have ranged from incredibly microscopic, smaller than an atom, to perhaps the mass of a small asteroid. The truly revolutionary aspect of this theory lies in what happens to these tiny black holes. According to Stephen Hawking's groundbreaking work, black holes aren't entirely black. They slowly evaporate over time by emitting what's known as Hawking radiation. The smaller a black hole, the faster it evaporates. So these primordial mini black holes, if they existed, would have had incredibly short lifespans, burning off their mass in a burst of high-energy particles. As one of these primordial black holes rapidly evaporated, it wouldn't just vanish into thin air. Instead, it would create an incredibly extreme environment, a superheated, dense plasma packed with fundamental particles right in the heart of the expanding universe. Think of it like a localized miniature Big Bang happening again and again, but on a much smaller scale. In these fleeting, fiery bursts, the conditions could have become ripe for novel particle interactions. The extreme temperatures and pressures generated during the final moments of a primordial black hole's evaporation, or perhaps even in the dense accretion disks that might have formed around them, could have acted as unique nuclear foundries. While Big Bang nucleosynthesis focused on hydrogen and helium, The unique dynamics inside and around evaporating primordial black holes might have allowed for the formation of slightly heavier elements, perhaps even up to lithium, beryllium, or boron, in quantities different from standard predictions. Some even speculate that these microfactories could have produced trace amounts of elements that are not easily explained by standard stellar nucleosynthesis, or even provided seeds for the formation of the first stars and galaxies by creating density perturbations in the early universe. It's a fascinating thought, suggesting that the universe's first atoms might trace their lineage not just to the Big Bang itself, but also to the explosive demise of these mysterious ancient cosmic remnants. While primordial black holes offer a fascinating, albeit speculative, detour in our cosmic story, our next theory takes us into an even more enigmatic realm, the invisible, pervasive presence of dark matter. We know dark matter exists because of its gravitational pull on galaxies and galaxy clusters, but we have yet to directly detect it or understand its fundamental nature. It makes up about 27% of the entire universe, dwarfing the ordinary matter that forms stars, planets, and us. So, if this mysterious substance is so abundant, could it have played a direct, perhaps even catalytic, role in the formation of the very first atoms? This brings us to the intriguing concept of dark matter interactions and its potential influence on early universe chemistry. Imagine for a moment that dark matter isn't just a passive gravitational scaffold for the universe, but an active, if subtle, participant in the grand ballet of creation. Some cutting-edge theories propose that exotic dark matter particles, unlike the familiar protons and neutrons, could have interacted with each other or even with regular matter in ways that profoundly influence the conditions necessary for atom formation. For instance, consider models where dark matter particles, in their own unique interactions or perhaps through their eventual decay, released bursts of energy. This energy, even if minuscule on a cosmic scale, could have momentarily altered the local conditions in the primordial soup. Perhaps these interactions provided just the right temperature or pressure fluctuations to encourage protons and neutrons to bind, or even to stabilize fleeting intermediate particles that were crucial for these early atomic reactions. It's like adding a hidden catalyst to a chemical experiment, subtly nudging the reaction along. Other fascinating hypotheses suggest that certain types of dark matter particles might have served as a kind of scaffolding or template for the assembly of ordinary matter. Picture a scenario where these dark matter particles, being much heavier or having different properties than regular matter, created localized density enhancements or energy wells. These regions could have acted as gravitational traps or energy sinks, pulling in nearby protons and neutrons and effectively increasing their concentration in specific areas. In such dense pockets, the likelihood of successful fusion events, like the formation of deuterium or helium, would significantly increase. It's a bit like having microscopic gravitational magnets attracting the building blocks of atoms, making it easier for them to find each other and combine. Furthermore, some speculative models delve into the idea of dark chemistry, where dark matter particles might have their own set of interactions and reactions, forming what are sometimes called dark atoms or dark nuclei. While these dark structures wouldn't directly form the familiar atoms of hydrogen or helium, their presence and decay could have indirectly affected the environment for ordinary matter. For example, the decay products of certain dark matter particles could include high-energy photons or other fundamental particles that then interact with ordinary matter, influencing its temperature, density, or even stability. This could have either accelerated or slowed down the processes of Big Bang nucleosynthesis, leading to slightly different abundances of light elements than predicted by standard models, or perhaps even explaining some of the subtle anomalies observed in the universe's oldest compositions. It's a tantalizing thought that the very fabric of reality, including the creation of atoms, might be intrinsically linked to this elusive, invisible component of our universe. While the discussion of dark matter leads us into the realm of the unseen, our next hypothesis dares to ask an even more profound question. What if the Big Bang wasn't the absolute beginning, but rather a dramatic transformation of something that already existed? This takes us to the truly mind-bending concept of a pre-Big Bang cosmic foam. Picture for a moment not a singular origin point, but an eternal, seething, chaotic sea of pure energy. In this incredibly abstract landscape, the very fabric of spacetime might not have been smooth and predictable, but rather a frothing, bubbling foam where tiny regions continuously appeared and disappeared, undergoing rapid, violent fluctuations on a quantum level. This isn't just about an empty void, it's about a dynamic, living, pre-cosmic state filled with potential and governed by rules far beyond our everyday experience. Within this bubbling quantum foam, the idea is that virtual particles, those ephemeral entities that constantly pop into and out of existence in even seemingly empty space, could have played a crucial role. In the everyday vacuum, these particles annihilate each other almost immediately. But in a pre-Big Bang state, under extreme conditions of quantum gravity and energy, it's theorized that some of these fluctuations might have grown exponentially, becoming real, stable particles. Think of it like boiling water. Most bubbles pop, but occasionally one grows large enough to survive and rise to the surface. Similarly, in the cosmic foam, a favorable combination of quantum jitters could have allowed a pocket of energy to spontaneously condense into distinct particles, providing the very first seeds for matter. This would be a process of continuous creation and annihilation, a cosmic dance where the stage itself is constantly morphing. This truly radical idea finds some of its roots in cutting-edge theories like quantum gravity and string theory, which attempt to unify the laws of the very large, like general relativity, with the laws of the very small, like quantum mechanics. These theories suggest that at unimaginably tiny scales, spacetime itself might not be smooth but rather granular or foamy. Within this framework, the Big Bang could be reinterpreted not as an explosion from nothing, but as an energetic phase transition within this pre-existing cosmic foam. Perhaps a particularly large or stable fluctuation simply reached a critical point, expanding rapidly and cooling to form the universe we observe today. So, the first atoms, or at least their fundamental precursors, wouldn't have been born in the Big Bang itself, but rather emerged from the inherent instability and creative potential of this earlier, primordial state. They would be the direct descendants of these quantum fluctuations, the first tangible manifestations of energy coalescing into form. Consider the profound implications of this. If the universe emerged from a pre-existing foam, it opens up the possibility of multiple Big Bangs or cyclical universes, where expansion and contraction are just different phases within this eternal cosmic froth. It implies that the particles we are made of, and indeed the entire universe, could be the result of a spontaneous, almost organic process of self-organization arising from the very fundamental nature of reality, long before the familiar laws of physics solidified. This makes the formation of the universe's first atoms not a singular event in time, but a continuous evolution, a ripple in an infinitely deep and ancient cosmic ocean, where the seeds of everything, including hydrogen and helium, were sown in the very fabric of a constantly bubbling pre-cosmic soup. If the pre-Big Bang foam hypothesis expands our view of the universe's origin, our next theory stretches the boundaries of reality even further, suggesting that our universe might just be one of countless others. This brings us to the truly mind-bending concept of the multiverse and atomic replication. Imagine not just one Big Bang, but an infinite number of them, each spawning its own unique universe with its own set of fundamental physical laws and constants. If this is true, then the conditions that led to the formation of the universe's first atoms here in our cosmic neighborhood might not be unique to us, but rather a reflection of a grander cosmic natural selection at play across a vast, unimaginable tapestry of realities. In this speculative but deeply intriguing scenario, the parameters that allowed for stable atoms to form the precise strength of the strong nuclear force that binds protons and neutrons, the exact mass of an electron, the delicate balance of fundamental constants aren't just lucky coincidences. Instead, they become a sort of cosmic lottery. Think about it. If there are myriad universes, each with slightly different physical laws governing its existence, then some of these universes would inevitably be sterile, unable to form anything more complex than a chaotic soup of particles. In such universes, perhaps the strong nuclear force is too weak to hold nuclei together, or particles are too short-lived to coalesce. Life, stars, and even basic elements beyond hydrogen would be impossible. However, in other universes, like our own, the fundamental constants would be perfectly tuned for complexity to emerge. This tuning allows for the stable formation of hydrogen and helium, the precursors to stars, and eventually the heavier elements that make up planets and life. This isn't necessarily a conscious design, but rather a consequence of what's often called the Anthropic Principle in a multiverse context. We observe a universe capable of supporting life because we exist to observe it. If our universe wasn't capable of forming atoms, we wouldn't be here in the first place to ask these questions. It's a bit like finding yourself in a room with oxygen and assuming every room in the house has oxygen, when in fact you're only in the one specifically designed to allow you to breathe. The implication for the universe's first atoms is profound. It suggests that their very existence, their stability, and their abundance aren't just a local phenomenon of our Big Bang, but potentially a successful replication of atomic conditions across cosmic scales. In this view, the ability of our universe to produce stable atoms like hydrogen and helium isn't singular. It's an outcome that is constantly being experimented with and refined across countless other universes. Those that succeed in creating atomic structures capable of forming stars and eventually life are the ones that persist and evolve into complex cosmic structures. The others, the ones where the atomic dice roll came up uninhabitable, simply fade away or remain as formless energy, never developing the intricate chemical reactions that lead to complexity. So, the formation of the universe's first atoms becomes less of a unique event and more of a successful instance of cosmic fine-tuning, replicated and refined across an endless expanse of parallel realities. While the multiverse theory expands our cosmic address book to an unimaginable degree, our next theory brings us back to the very first moments of our own universe, offering a powerful explanation for how the raw materials for atoms initially appeared. This is the theory of inflationary field decay, and it's a cornerstone of modern cosmology, helping to explain many of the universe's most puzzling features, including its incredible homogeneity and flatness. To understand this, we need to picture the universe just a tiny fraction of a second after the Big Bang, far, far earlier than the 1-second mark we discussed with Big Bang nucleosynthesis. In this incredibly brief but utterly transformative period, the universe is thought to have undergone an exponential growth spurt, expanding faster than the speed of light itself. This isn't just regular expansion, it's cosmic inflation. What drove this unimaginable burst of expansion? Scientists propose a hypothetical energy field, often called the inflaton field. Think of it like a temporary, exotic form of energy that permeated the entire universe. As long as this inflaton field was switched on, it created a repulsive gravitational force pushing space-time apart at an astonishing rate. It's like blowing up a balloon so fast that any wrinkles or imperfections on its surface are stretched out and smoothed away, leading to the remarkably uniform universe we observe today. During this inflationary epoch, the universe would have been incredibly cold and essentially empty of matter, filled only with the energy of this inflaton field. It was a period of pure energetic potential humming with latent power, but inflation couldn't last forever, At some point, the inflattened field had to switch off, or more accurately, decay. Imagine a ball rolling down a hill. As it reaches the bottom, its potential energy is converted into kinetic energy. In a similar way, as the inflattened field rolled down its energy potential, its vast energy was suddenly released. This is the crucial moment for the formation of the universe's first particles. This rapid decay didn't just dissipate, it unleashed a torrent of energy, converting the smooth, uniform energy of the inflattened field into a hot, dense soup of fundamental particles. This process is often called reheating, because it's at this point that the universe transitions from its cold, inflationary state to the hot, dense plasma that we associate with the traditional Big Bang. So, the matter we are made of, the quarks and leptons that would eventually form protons and neutrons, are theorized to have been born directly from this inflationary field decay. The energy of the inflattened field literally materialized into these particles. It's a profound idea. The very fabric of space-time, through the action of this ephemeral field, gave rise to the building blocks of matter and energy. This means that the universe went from a state dominated by a single, peculiar energy field to one teeming with the diverse particles that would eventually cool, coalesce, and interact to form hydrogen and helium atoms. The elegance of this theory is that it doesn't just explain the conditions for atom formation. It directly explains the very existence of matter in the first place, linking the initial structure of the cosmos to the fundamental particles that compose it. Without this initial burst of particle creation from the decaying inflattened field, there would have been no quarks, no leptons, and consequently, no protons, no neutrons, and ultimately, no first atoms to begin the cosmic story. While inflationary field decay brilliantly explains the origin of the universe's fundamental particles, our journey now takes an even more abstract turn, diving into the potential role of exotic, highly theoretical structures that might have been imprinted on the very fabric of spacetime during the universe's infancy. This brings us to the fascinating, almost science fiction-like concept of topological defects as catalysts. Imagine the early universe not as a smooth, uniform expanse, but as a space that underwent rapid, dramatic phase transitions, much like water freezing into ice. As water cools, ice crystals form, and where these crystals meet, they can create defects, boundaries, lines, or points where the crystalline structure is imperfectly aligned. Cosmologists theorize that similar defects could have formed in the early universe as fundamental forces separated from a unified superforce. These are not flaws in a negative sense, but rather inherent features of how the universe might have organized itself. We're talking about incredibly strange entities like cosmic strings, magnetic monopoles, and domain walls. Cosmic strings, for example, are theoretical one-dimensional defects like infinitely thin, immensely dense lines stretching across the cosmos. Monopoles are point-like defects, essentially isolated north or south magnetic poles, something never observed in our current universe where magnets always have both poles. Domain walls are two-dimensional, like vast, thin membranes separating regions of space with different physical properties. These defects are hypothesized to be incredibly massive, carrying immense energy, and could have persisted since the Big Bang, relics of a time when the universe was undergoing profound changes in its fundamental physics. If they exist, they would represent incredibly dense, high-energy regions, fundamentally different from the surrounding spacetime. So, how could these exotic structures have acted as catalysts for the formation of the universe's first atoms? Picture a cosmic string, a super-dense filament slicing through the primordial plasma. Its immense gravitational pull would have acted like a cosmic magnet, drawing in vast amounts of surrounding matter and energy. This localized concentration of particles would have created regions of extreme density and pressure, far exceeding the average conditions of the early universe. In these hotspots along the string, the rate of nuclear fusion, the process that formed hydrogen and helium, could have been significantly accelerated. It's like having mini-universes within our universe, each with its own intense atom-forging furnace. The sheer energy gradients around such defects could have provided the precise conditions needed for certain nuclear reactions to occur more frequently or efficiently than in the general cosmic background. Furthermore, some theories suggest that topological defects might have possessed unique electromagnetic or gravitational properties that directly influenced particle interactions. A magnetic monopole, for instance, could have concentrated magnetic fields to an extreme degree, potentially affecting the spins and alignments of protons and neutrons in ways that favored their binding. Imagine these defects acting as scaffolding or even as tiny cosmic factories where the fundamental building blocks of matter were more likely to collide and fuse. They might have created pressure cookers where the conditions were just right for hydrogen and helium to form at an accelerated rate, or perhaps even in slightly different proportions than predicted by standard Big Bang nucleosynthesis. If these defects played such a role, their influence would not only explain the formation of the first atoms, but also potentially illuminate some of the earliest large-scale structures in the universe, as matter would have preferentially clumped around these cosmic blemishes. This theory opens a door to a universe where the initial distribution and composition of atomic building blocks were not perfectly uniform, but were profoundly shaped by these strange, ancient remnants of the universe's most dramatic phase transitions. From the highly concentrated energy of topological defects, we now shift our focus to something far more subtle yet equally profound: the very rules governing the universe. Our next theory dives into a truly fascinating what-if scenario, exploring the possibility that the fundamental constants of physics weren't always so constant. This brings us to the intriguing idea of varying fundamental constants and their potential impact on the universe's first atoms. Imagine a universe where the numbers defining reality, like the strength of electromagnetism, the force that binds electrons to nuclei, or the gravitational constant that dictates how masses attract, weren't fixed values from the get-go. Instead, what if they subtly changed, even just a tiny bit, during the extreme conditions of the early universe? The implications for atom formation would be nothing short of revolutionary. To fully grasp the weight of this idea, let's consider a few examples of these so-called constants. Take the fine structure constant, for instance. This dimensionless number, roughly 1 divided by 137, dictates the strength of the electromagnetic interaction. It determines how tightly electrons are bound to atomic nuclei. If this constant were even slightly different, say a tiny bit larger, electrons would be pulled much more strongly towards the nucleus. This might make atoms incredibly small and dense, or it could even lead to instability, causing electrons to literally collapse into the nucleus, preventing the formation of stable atoms altogether. Conversely, if the fine structure constant were marginally smaller, electrons might not be bound strongly enough, simply drifting away from protons, meaning no atoms could ever form. It's a delicate cosmic tightrope walk, and our universe seems to have landed perfectly in the sweet spot. Now, extend this concept to other constants. Consider the ratio of the proton mass to the electron mass, or the strength of the strong nuclear force responsible for holding atomic nuclei together. If this force were just a few % weaker, atomic nuclei beyond hydrogen, like helium or lithium, might never have formed, leaving the universe a bland, structureless expanse of only protons and electrons. If it were slightly stronger, however, protons might have bound too tightly, forming complex, stable nuclei so readily that hydrogen, the fuel for stars, would be scarce. The universe would then burn out quickly, or perhaps never even ignite in the first place. The very existence of stars, and consequently the heavier elements forged within them, hinges on these incredibly precise values. The theory of varying constants suggests that in the chaotic, high-energy environment of the early universe, these constants might not have settled into their current values immediately. Perhaps they were dynamic fields themselves, slowly evolving or fluctuating. This evolution could have profoundly influenced the conditions under which Big Bang nucleosynthesis occurred. A transient change in one of these constants could have, for example, accelerated or decelerated the rate of nuclear fusion, changed the binding energies of light nuclei, or even altered the stability of protons and neutrons. This isn't just about minor adjustments. Even a minute deviation from the currently observed values could mean the difference between a universe teeming with atoms and a universe unable to form any stable matter at all. This perspective offers an intriguing answer to the question of why our universe is so incredibly adept at forming stable matter and, in turn, structured cosmic objects like stars and galaxies. It suggests that the atomic recipe wasn't simply a given at the Big Bang, but perhaps the outcome of a dynamic process where the fundamental rules themselves were being established. If these constants indeed varied, then their settling into the precise values we observe today would have been a crucial step, essentially fine-tuning the universe for the eventual formation of stars, planets, and life. It implies a kind of cosmic evolution even at the most fundamental level, where the very laws of physics that govern particle interactions were themselves honed to allow for the rich complexity of the cosmos we inhabit. The stability and abundance of the universe's first atoms might not just be a consequence of the Big Bang's initial temperature and density, but also a testament to a cosmic process that carefully calibrated the underlying rulebook for existence. While the concept of varying fundamental constants hints at a universe whose rules were still being written, our next theory takes a more philosophical yet deeply scientific stance. It suggests that the formation of the universe's first atoms wasn't simply a matter of chance collisions or specific conditions, but rather an intrinsic tendency built into the very fabric of reality itself. This brings us to the profound idea of self-organizing principles of matter. Imagine the universe not as a passive stage where particles randomly bump into each other, but as an active system with an inherent drive towards greater complexity and order. This perspective posits that the fundamental laws of physics aren't just descriptions of nature. They inherently encourage the formation of stable, intricate structures, with atoms being among the very first and most crucial examples. To understand this, let's consider the concept of emergent complexity. In many natural systems, simple rules and components can give rise to incredibly complex and organized patterns. Think of a snowflake with its intricate symmetrical structure forming from simple water molecules, or a bustling ant colony, where highly organized behavior emerges from individual ants following basic rules. The theory of self-organizing principles suggests that the early universe might have operated on a similar premise. The fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, along with the properties of the elementary particles, could be so finely tuned that they naturally funnel energy and matter towards states of increasing organization. Rather than a purely random scattering of protons, neutrons, and electrons, the universe might have possessed an innate urge to form the most stable and fundamental building blocks, atoms. This isn't about some mystical force guiding cosmic evolution. It's about the inherent mathematical elegance and stability built into the laws of physics themselves. For instance, the fact that hydrogen and helium are incredibly stable configurations of protons, neutrons, and electrons is not accidental. The energy levels of these simple atoms are such that once formed, they are highly resistant to breaking apart. It's energetically favorable for protons and electrons to combine into hydrogen atoms, and for protons and neutrons to form helium nuclei given the right temperature and density. The universe spontaneously found these lowest energy states, which happened to be atoms, because the laws of physics guided it there. It's a natural progression from a higher energy, less organized state to a lower energy, more organized state, much like water flowing downhill. Furthermore, this perspective emphasizes a deeper order to the universe's early evolution, suggesting that the drive towards atomic formation was not just a fleeting 20-minute window after the Big Bang, but an underlying principle that continues to shape the cosmos. The very stability of atoms once formed allowed for the gradual clumping of matter that led to the first stars, then galaxies, and eventually planets. The self-organizing principle isn't just about the initial formation of hydrogen and helium. It's about the universe's continuous tendency to build upon existing structures. Once atoms formed, they provided the stable scaffolding upon which the next layers of complexity could emerge: molecules, dust, nebulae, and eventually the intricate cosmic structures we observe today. It implies that the universe wasn't just a place where atoms happened to form, but a place designed in its very fundamental laws to encourage their formation, enabling the entire cosmic saga of stars, planets, and life to unfold. While self-organizing principles hint at an inherent order, our next theory brings us back to the initial chaos, delving into a phase of the early universe so extreme that it's challenging to even imagine. Before hydrogen and helium atoms, before even protons and neutrons as we know them, the universe existed as an unimaginably hot, incredibly dense soup. This brings us to Theory 10, quark-gluon plasma condensation. If the Big Bang was the ultimate explosion, then what immediately followed was a state of matter unlike anything we typically encounter today. We're talking about temperatures in the trillions of degrees Celsius, where matter as we understand it simply couldn't exist. Picture the universe just microseconds after the Big Bang, perhaps 1/1,000,000th of a second old. At this point, the cosmos was utterly dominated by what physicists call a quark-gluon plasma. In this bizarre state, quarks, the fundamental particles that usually make up protons and neutrons, were not bound together. Instead, they zipped around freely, swimming in a sea of gluons, the force-carrying particles that mediate the strong nuclear force. Imagine a kind of primordial, perfect liquid where the building blocks of matter were utterly deconfined. It's a state of matter so exotic that scientists can only recreate it for fleeting moments in massive particle accelerators like the Large Hadron Collider, by smashing atomic nuclei together at nearly the speed of light. These experiments provide crucial insights into how this early universe might have behaved. As the universe expanded, it also began to cool, albeit rapidly. This cooling was the critical factor that triggered a profound phase transition, much like steam condensing into water or water freezing into ice. As the temperature dropped to a critical point around 2 trillion degrees Celsius, still unimaginably hot but cool enough for this transformation to occur, the strong nuclear force carried by the gluons exerted its dominance. The previously free-floating quarks and gluons began to condense and confine themselves into stable packets of matter. This process, known as hadronization, is how the first composite particles, specifically protons and neutrons, were born. Each proton formed from 2 up quarks and 1 down quark, while each neutron formed from 1 up quark and 2 down quarks. It was a moment of immense structural change where the fundamental constituents of matter locked into definite, stable configurations. This meticulous description of quark-gluon plasma condensation is crucial because it provides the foundational understanding of how the very building blocks of atomic nuclei came into existence. Without this phase transition, without the quarks and gluons confining themselves into protons and neutrons, there would be no particle stable enough to eventually form hydrogen and helium. The forces at play during this condensation were precisely calibrated. The strong nuclear force had to be just the right strength to bind the quarks reliably, but not so strong that it created overly massive or unstable combinations. It was a cosmic forging process where the raw, undifferentiated energy of the early universe was transformed into the distinct, fundamental particles that would later serve as the foundation for all known matter. This theory gives us a glimpse into a universe so hot and dense that even the most basic forces behave differently, shaping the very essence of matter from a primordial, perfect fluid into the particles that would define everything that came after. While the quark-gluon plasma gave us protons and neutrons, and Big Bang nucleosynthesis forged hydrogen and helium, our cosmic story isn't quite complete without acknowledging the presence of a truly enigmatic particle that could have subtly influenced the entire process, the neutrino. These ghostly particles are incredibly elusive, almost massless, and interact very rarely with other matter. Yet they are astoundingly abundant, outnumbering protons and neutrons in the universe by a vast margin. This brings us to a compelling, albeit less frequently discussed idea: neutrino-driven nucleosynthesis. Could these seemingly insubstantial particles have played a more significant role in the early universe's atomic alchemy than we previously imagined? To understand their potential impact, we need to recall the conditions just moments after the Big Bang, precisely when protons and neutrons were forming from the quark-gluon plasma. At this point, the universe was so hot and dense that neutrinos were in constant, vigorous interaction with protons and neutrons, along with electrons and positrons. These interactions were mediated by the weak nuclear force, one of the four fundamental forces of nature. Here's where it gets interesting. Neutrinos can transform protons into neutrons, and antineutrinos can transform neutrons into protons. Think of it like a cosmic balancing act. In the very early universe, these transformations happened so rapidly that the number of protons and neutrons was roughly equal. However, as the universe continued to expand and cool, these neutrino interactions became less frequent. This gradual decoupling of neutrinos from the rest of the cosmic soup had a critical consequence. It locked in a specific ratio of protons to neutrons. Since neutrons are slightly heavier than protons, they are inherently less stable and tend to decay into protons if left alone. The neutrino interactions, while they were occurring, helped to maintain a delicate equilibrium. But once these interactions ceased to be efficient, around 1 second after the Big Bang, the neutron-to-proton ratio became fixed. This ratio was approximately 1 neutron for every 7 protons. This number is absolutely crucial because it directly determined how much helium could form during Big Bang nucleosynthesis. Remember, helium-4 consists of 2 protons and 2 neutrons. If there were too few neutrons, not enough helium could be made. If there were too many, the universe would have ended up with a vastly different composition. The neutrino-driven nucleosynthesis theory suggests that subtle variations in neutrino properties or their interactions could have nudged this sacred neutron-to-proton ratio one way or another, even slightly. For example, if there were unknown types of sterile neutrinos, or if neutrinos possessed slightly different mass hierarchies than currently understood, their interactions could have skewed the balance. Imagine a scenario where a particular neutrino interaction was slightly more efficient at converting protons to neutrons or vice versa, just before the freeze-out point. Even a minute alteration in this ratio could lead to perceptible differences in the predicted abundances of not just helium, but also trace elements like deuterium and lithium-7. Astronomers are constantly refining measurements of these light element abundances in the oldest, most pristine parts of the universe. Any tiny discrepancy between observation and the standard Big Bang nucleosynthesis predictions could be a clue pointing towards these subtle neutrino influences. Furthermore, some speculative models propose that neutrinos, despite their elusive nature, might have played an even more active role in the very early universe, perhaps influencing the conditions for nucleosynthesis in ways we don't yet fully comprehend. For example, if neutrinos had slightly stronger interactions, or if they clustered in certain ways, they might have created localized density fluctuations that subtly affected nuclear reaction rates. It's a complex interplay, adding another layer of intricate detail to the cosmic history of atom formation. While the established model of Big Bang nucleosynthesis is remarkably successful, the ongoing study of neutrinos, their properties, and their interactions reminds us that even when we think we have a solid understanding, there might always be unseen forces like these ghostly particles, subtly steering the cosmic ship, adding another layer of complexity and wonder to the story of how the universe's first atoms came to be. While neutrinos present a subtle influence, our next theory plunges us into an idea so radical that it forces us to reconsider the very architecture of reality itself. What if the universe isn't just three spatial dimensions, but many more? This brings us to a captivating, deeply speculative concept: extra dimensions and atomic stability. Imagine for a moment that besides the familiar length, width, and height, there are other dimensions curled up so tightly that we can't perceive them with our senses or even our most powerful microscopes. String theory, a leading candidate for a theory of everything, posits the existence of 6 or 7 such extra-spatial dimensions, in addition to the 4 three-spatial plus 1 time that make up our perceived spacetime. These hidden dimensions are thought to be incredibly tiny, compactified or unfurled at scales far smaller than an atom. But could their presence, especially during the tumultuous, incredibly high energy conditions of the early universe, have profoundly influenced the stability or even the formation mechanisms of the very first atoms? Let's unpack this. If extra-spatial dimensions exist, they wouldn't just be inert background scenery. Their geometry and dynamics could directly impact the fundamental forces of nature. Think about gravity and electromagnetism. In our familiar 3 spatial dimensions, the strength of these forces drops off pretty consistently with distance. But if there were extra dimensions, the forces might propagate differently within them. For instance, gravity, being the weakest of the fundamental forces in our 4-dimensional spacetime, theoretically permeates all dimensions. If these extra dimensions were ever large or dynamic in the very early universe, even for an incredibly brief period, gravity might have been much stronger than we perceive it to be today. A stronger gravitational force could have influenced the density of particles, perhaps even creating localized regions of extreme pressure that would have aided in nuclear fusion or particle confinement. It's like having force fields that extend into hidden rooms, subtly altering how things behave in the visible space. The interplay between these dimensions and the fundamental forces could also have affected the other forces crucial for atom formation. The electromagnetic force, for example, which governs how electrons bind to nuclei, might have had a different effective strength if it too could leak into these extra dimensions. Even a slight variation in its characteristics during the early universe could alter the energy levels of electrons in potential atomic structures, making nascent atoms either more or less stable. Similarly, the strong nuclear force, which holds protons and neutrons together in atomic nuclei, could have been influenced by the geometry of these higher dimensions. If the strong force were momentarily stronger or weaker due to these extra dimensions, it could change the binding energies of the first atomic nuclei, altering the precise conditions required for hydrogen and helium to form stably. Consider a speculative scenario. Perhaps in the very first instance after the Big Bang, these extra dimensions were not fully compactified. Perhaps they were briefly unfurled, allowing for different physical laws to manifest before they rapidly curled up to their unimaginably small sizes. During this unfurling or compactification process, the very nature of matter and energy might have been subtly different. Quantum fluctuations within these transiently larger extra dimensions could have led to unique particle interactions or even the creation of specific types of particles that later played a crucial role in forming stable atoms. It's a bit like a malleable cosmic fabric, where the rules of the game are being set as the fabric itself folds and unfolds. The process of these dimensions shrinking could have released energy that contributed to the reheating of the universe, providing the thermal energy necessary for particles to interact and form the first stable nuclei. This theory offers a fascinating, almost artistic, explanation for the fine-tuning of the universe's fundamental constants. Instead of them being fixed from the absolute beginning, their values could be a consequence of how these extra dimensions compactified. The way these dimensions curled up might have determined the precise strength of electromagnetism or the strong nuclear force that we observe today, essentially dictating the very possibility of stable atoms. If this were the case, then the formation of the universe's first atoms, their precise properties, and their very existence would be inextricably linked to the unseen architecture of reality, a testament to a cosmic dance where the dimensions themselves choreographed the initial steps of atomic creation. It adds a layer of profound mystery and complexity to the foundational moments of our universe, suggesting that the familiar building blocks of matter are deeply intertwined with spaces beyond our immediate perception. While extra dimensions hint at hidden architectural blueprints for the universe, our next theory brings us back to something more tangible, though still elusive: immense, invisible forces that could have sculpted the very first atomic landscapes. We're going to explore the intriguing potential of cosmic magnetic fields as scaffolds. Imagine the universe just moments after the Big Bang, filled not just with a uniform plasma, but also crisscrossed by vast primordial magnetic fields. These aren't the localized fields you find around a bar magnet or a planet. These are fields spanning truly cosmic scales, originating from processes occurring in the very earliest and most energetic phases of the universe. Though their exact origin is still a topic of intense research, theories suggest they could have been generated by turbulent plasma motions, phase transitions, or even exotic mechanisms during inflation. If these pervasive magnetic fields indeed existed, they wouldn't have been mere background noise. They could have exerted a powerful, organizing influence on the nascent universe, effectively creating invisible scaffolding that guided the formation of the first atoms. Think about how a magnetic field works. It exerts a force on moving charged particles, deflecting their trajectories. In the early universe, the cosmos was a superheated plasma, teeming with free-floating charged particles like electrons, protons, and other ions. If strong, large-scale magnetic fields were present, they would have continuously corralled these charged particles, pushing them around and concentrating them in certain regions. Instead of randomly diffusing throughout the nascent cosmos, these particles would have been funneled along the magnetic field lines, much like iron filings aligning along the lines of force around a magnet. This constant guiding and concentrating action would have led to localized regions of higher density within the plasma. These densely packed pockets would have been natural cosmic nurseries where atom formation was not just probable but significantly enhanced. The increased density would mean that protons, neutrons, and electrons were much more likely to encounter each other and undergo the necessary nuclear fusion reactions to form the first hydrogen and helium nuclei. Furthermore, these cosmic magnetic fields could have influenced the early universe in ways that explain some of the large-scale structures we observe today. Imagine these magnetic field lines creating subtle yet persistent inhomogeneities in the early cosmic soup. Where the field lines converged, matter would clump. Where they diverged, regions would be less dense. This would essentially create a pre-existing cosmic web, a skeletal framework of higher and lower density regions, even before gravity had sufficient time to build up significant structures. These early overdensities, subtly sculpted by magnetic fields, could then have served as the gravitational seeds for the very first stars and galaxies. The initial formation of hydrogen and helium atoms within these magnetically induced dense pockets would thus be inextricably linked to the subsequent formation of cosmic structures. The efficiency of Big Bang nucleosynthesis and the precise abundance of light elements could have been mildly altered within these localized, magnetically enhanced regions, leading to subtle variations that might even be detectable in the cosmic microwave background radiation or in the most pristine, ancient gas clouds. The beauty of this theory lies in its ability to connect various cosmic phenomena. It suggests that the primordial magnetic fields didn't just passively exist, they were active architects shaping the distribution of matter and energy from the very beginning. They might have directly influenced the speed and efficiency with which protons and neutrons fused, creating environments where atomic nuclei could form more readily. It's almost as if the universe had a built-in guidance system, subtly directing the flow of primordial particles, preparing the ground for the creation of the fundamental building blocks of everything we see around us. The first atoms in this view were not just a product of uniform expansion and cooling, but also of an invisible, pervasive magnetic scaffold that guided their very birth, laying down the pattern for the vast cosmic tapestry that would unfold over billions of years. While cosmic magnetic fields suggest an invisible scaffold for matter, our next theory takes us to a realm so fundamental, so tiny, and so chaotic that it forces us to confront the very limits of our understanding of physics. We're venturing into the truly mind-bending world of quantum gravity fluctuations and their potential role in the genesis of the universe's first atoms. Imagine the universe not just moments after the Big Bang, but before the Big Bang as we typically conceive it, in an epoch so incredibly early that space, time, and matter as we know them might not have even fully formed. This is the realm of Planck-scale physics, where the universe was compressed to an unimaginably small size, a region so tiny that quantum effects of gravity become dominant, leading to a space-time that is anything but smooth and predictable. At this Planck scale, approximately 10 to the power of -35 meters, that's a decimal point followed by 34 zeros and then a 1. The very fabric of space-time is no longer a calm, continuous canvas. Instead, it's theorized to be a seething, turbulent foam, a froth of incessant quantum fluctuations. Think of it like boiling water, but instead of water molecules, it's space-time itself bubbling and popping, with tiny wormholes and exotic geometries constantly appearing and disappearing. Our familiar laws of physics, general relativity, and quantum mechanics break down here. Neither fully describes what's happening in this arena where gravity is incredibly strong but also subject to quantum uncertainty. It's a place where the lines between energy, matter, and the geometry of space-time become incredibly blurred, perhaps even interchangeable. The radical idea behind this theory is that the first atoms, or more accurately, their fundamental precursors, didn't form in a pre-existing space and time, but rather emerged directly from the violent, chaotic dynamics of this quantum foam. In this scenario, the initial state of the universe wasn't a singularity that exploded, but rather a transition, a kind of crystallization of space-time itself. Imagine this quantum foam as a highly energetic, unstable medium. As the universe began its expansion, or perhaps underwent a phase transition from this chaotic state, these quantum fluctuations could have settled down. Just as water freezes from a liquid into an ordered crystalline structure, the turbulent quantum foam might have frozen or condensed into the smoother space-time we know, simultaneously giving rise to pockets of stable energy that materialized into fundamental particles. These initial particles wouldn't have been floating in space, they would have been inextricably linked to the very structure of the emerging space-time. In this view, the universe's first quarks and leptons, and subsequently the protons and neutrons that would form hydrogen and helium, were not merely created in space-time, but were in a sense emergent properties of spacetime's transition from a quantum gravitational state. The energy of these fluctuations directly converted into the mass and energy of elementary particles. It's a profound thought that the very existence of matter, the building blocks of everything, is fundamentally intertwined with the quantum nature of gravity itself. This theory pushes the boundaries of our imagination, suggesting that the familiar components of our universe, including atoms, are the solidified remnants of an unimaginably violent primordial dance of space-time, where the universe literally gave birth to itself, creating the fundamental particles by smoothing out its own chaotic nature. While quantum gravity fluctuations suggest an internal, self-creating aspect to the universe, our next theory spins a cosmic narrative that is truly cyclical, proposing that the atoms around us might carry echoes of a past so ancient it predates our very Big Bang. This journey takes us into the profound, almost poetic concept of a bouncing universe, where the ending of one cosmic cycle provides the fiery genesis for the next. Imagine the universe not as a singular event, but as an infinite series of Big Bangs and Big Crunches, a grand cosmic breath that endlessly expands and contracts. In this mind-bending scenario, our universe is just one chapter in an eternal cosmic saga, and the question arises, could the atoms of our universe, the very building blocks of stars, planets, and life, be recycled, re-energized, or even directly inherited from a previous cosmic cycle? This theory, often rooted in models like loop quantum cosmology or certain variations of string theory, challenges the notion of the Big Bang as an absolute beginning. Instead, it suggests that our universe didn't emerge from a singularity, but rather from the bounce of a universe that had previously undergone a big crunch, collapsing back in on itself after reaching its maximum expansion. As the previous universe contracted, its density and temperature would have soared to unimaginable extremes, perhaps even higher than those reached in our own Big Bang. But instead of collapsing into an infinitely dense point, the forces of quantum gravity or other unknown physics would intervene, preventing a true singularity and causing it to rebound, initiating a new phase of expansion, our Big Bang. It's a cosmic phoenix constantly reborn from its own ashes. The crucial implication for the universe's first atoms in such a model is truly fascinating. How much, if anything, could survive such a catastrophic crunch and fiery bounce? One possibility is that information, rather than physical particles themselves, could be preserved across cycles. The laws of physics, the fundamental constants, or even the underlying quantum states that dictate particle properties could somehow be encoded in the fabric of spacetime, carried through the crunch, and imprinted onto the new, expanding universe. This would mean that the conditions for forming hydrogen and helium, the precise energy levels, and the stability of atomic nuclei are not unique to our cycle, but are inherited parameters, fine-tuned by eons of cosmic evolution across countless previous bounces. It implies a kind of cosmic memory where the universe learns and refines its atomic blueprint with each rebirth. More radically, some versions of the bouncing universe theory even suggest that elementary particles themselves or their fundamental quantum properties could survive the crunch. Imagine that while larger structures like stars and galaxies would be totally pulverized, the most elementary particles, quarks, leptons, and even the force carriers might endure the immense pressure, perhaps transforming into a different state of matter before being re-energized and reformed in the subsequent bounce. This would mean that the raw material for our universe's first atoms, the very protons and neutrons that fused into hydrogen and helium, could literally be the descendants of particles from a previous cosmic incarnation. This cosmic inheritance would imply a deep continuity to matter, where the substance of the universe is not created anew with each Big Bang, but perpetually recycled, constantly renewing its atomic identity across an endless cycle of universal births and deaths. It adds a layer of ancient history to every atom, suggesting that the hydrogen in a distant star or the helium in a balloon could be as old as time itself, passed down from a universe that came before our own, a true echo from an infinite past. While a bouncing universe offers a cyclical dance of cosmic rebirth, our next theory shifts gears entirely. It doesn't propose a new mechanism for atom formation, but rather offers a profound, almost unsettling philosophical lens through which to view the very existence of those first atoms, the anthropic principle and atomic existence. This isn't a theory about how atoms came to be, but rather why they exist in a universe that allows us to ask such questions. Imagine a cosmic lottery where the very rules of reality are drawn from an infinite hat. The anthropic principle suggests that we observe a universe precisely because it's capable of supporting our existence, and the existence of atoms is absolutely fundamental to that capability. At the heart of this perspective lies what's often referred to as the fine-tuning problem. Take a moment to consider the fundamental constants of our universe, numbers like the strength of the electromagnetic force, the gravitational constant, the masses of elementary particles, and the precise conditions that allowed the Big Bang to unfold as it did. Scientists have calculated that even a minuscule variation in any one of these values would lead to a vastly different and likely sterile cosmos. For example, if the strong nuclear force, which binds protons and neutrons into atomic nuclei, were just 2% weaker, stable atoms beyond hydrogen might never have formed. The universe would be a desolate soup of free protons and electrons. Conversely, if it were slightly stronger, hydrogen wouldn't exist, as all protons would instantly fuse into heavier elements, rapidly burning out the universe before stars could even begin to shine. There would be no water, no complex chemistry, and certainly no life. The fine-tuning extends to every aspect. The specific balance between the electromagnetic force and the strong nuclear force is exquisitely tuned to allow carbon, the backbone of life, to form in stars. The mass difference between a proton and a neutron is crucial for proper Big Bang nucleosynthesis. If a neutron isn't slightly heavier than a proton, the universe would have collapsed quickly. The expansion rate of the universe itself is incredibly precise, too fast, and matter would have dispersed too quickly for galaxies and stars to form, too slow, and the universe would have collapsed back on itself before anything interesting could happen. These aren't just small margins. Often, the precision required is likened to hitting a target across the universe. So, how does the anthropic principle address this? It doesn't claim that the universe was designed for us or that it's a cosmic coincidence. Instead, the weak anthropic principle simply states that the conditions we observe in the universe must be compatible with the existence of intelligent observers. Because we exist, the universe must have the properties that allow for our existence. This creates a selection effect. Out of all possible universes, only those with the precise fundamental constants that allow for stable atoms, and subsequently stars, planets, and life, would ever contain observers to notice them. It's a bit like a fish wondering why its pond is perfectly suited for fish life. It never considers all the other bodies of water where fish couldn't survive. This perspective naturally leads into discussions about deeper cosmic implications. Is this fine-tuning merely cosmic luck, or does it hint at something more profound? Some argue that it strengthens the case for a multiverse, where countless universes exist with varying fundamental constants, and we simply happen to reside in one of the extraordinarily rare ones that hit the cosmic sweet spot for atom formation and life. Others suggest it points towards an underlying principle or even a grand design. Regardless of the interpretation, the anthropic principle profoundly impacts how we understand the genesis of the universe's first atoms. It shifts the question from merely how did they form to why did the universe allow them to form so perfectly. It highlights that the very possibility of particles binding into stable atomic structures is not a given, but a delicate balance woven into the very fabric of reality, a balance so precise that it allows for the vast cosmic tapestry we observe today, built one perfectly tuned atom at a time. While the anthropic principle offers a compelling why, our next theory dives deep into the how, proposing a universe far more elegant and musical than we can typically imagine. We're leaving the realm of point-like particles and diving into the incredibly complex yet beautiful world of string theory and fundamental vibrations. Forget everything you thought you knew about the basic building blocks of matter. In string theory, fundamental particles like quarks, electrons, and even the force-carrying photons aren't tiny, indivisible points. Instead, they are theorized to be incredibly tiny, one-dimensional vibrating strings, so infinitesimally small that they appear as points from our perspective. Imagine a cosmic orchestra where every particle is a different note, and the entire symphony of the universe is being played out by these vibrating strings. The revolutionary aspect of this idea lies in its simplicity and profound implications. Just as a violin string can produce different notes depending on how it vibrates, whether it oscillates gently or furiously, in simple or complex patterns, these fundamental cosmic strings are thought to produce different particles based on their unique vibrational modes. One specific vibrational pattern might manifest as an electron, another as a photon, and yet another as a quark. It's not about what a particle is in isolation, but how the string behaves. This elegant framework naturally unifies all fundamental forces, including gravity, in a way that traditional particle physics has struggled to achieve. The universe, in this view, is a vast, intricate tapestry woven from the vibrations of these fundamental strings, whose energy and patterns dictate everything we perceive as reality. For the formation of the universe's first atoms, this concept is nothing short of transformative. If all fundamental particles are various manifestations of vibrating strings, then the stability of protons, neutrons, and electrons, the very stability that allows them to combine into hydrogen and helium, is directly linked to the specific resonant frequencies of these strings. Imagine the early universe, incredibly hot and dense, filled with a cacophony of these vibrating strings. As the universe expanded and cooled, certain vibrational modes, those corresponding to stable particles like quarks and electrons, would have become energetically favorable. It's like a complex musical instrument tuning itself, settling into a stable, harmonious chord. These specific resonant frequencies would be the notes that constitute the building blocks of hydrogen and helium. The precise properties of these particles, their mass, charge, spin, are not arbitrary. They are determined by the unique way their underlying string vibrates. Furthermore, string theory often posits the existence of extraspatial dimensions, curled up in intricate geometries far beyond our perception. The way these strings vibrate, and thus the properties of the particles they form, could be profoundly influenced by the shape and dynamics of these hidden dimensions. Think of it like this: a violin string's sound isn't just determined by its length and tension, but also by the shape and material of the violin itself. Similarly, the specific vibrational patterns of the cosmic strings might be constrained or influenced by the geometry of these compactified extra dimensions. This implies a deep connection, the very properties that made hydrogen and helium stable and abundant. The precise masses of quarks, the strength of the strong nuclear force that binds them, could be a direct consequence of the shape and structure of these unseen dimensions. The universe's first atoms, therefore, wouldn't just be random assortments of particles, but perfectly tuned configurations arising from the resonant frequencies of fundamental strings, shaped and constrained by the geometry of a higher dimensional reality. It suggests that the cosmos, at its most fundamental level, operates like an immense, intricate symphony where the notes themselves are the particles, and the melody is the unfolding of the universe, with the first atoms representing its earliest, most stable chords. While string theory invites us to imagine a universe woven from vibrating filaments, our next theory takes that concept of higher dimensions and transforms it into a cosmic drama of immense proportions. What if our entire universe isn't just a four-dimensional spacetime, but merely a bubble or a sheet, a brain floating within a much larger, higher-dimensional space called the bulk? This brings us to a truly spectacular and profoundly influential idea: brain collisions and particle annihilation. Think of it like a cosmic version of two immense, invisible membranes adrift in an unimaginable void, suddenly slamming into each other. This isn't just science fiction, it's a cornerstone of what are known as ekpyrotic or cyclic models of cosmology, offering an alternative to the traditional Big Bang singularity. In these models, the Big Bang isn't the beginning of everything from nothing. Instead, it's the violent, energetic aftermath of a collision between two such three-dimensional brains, or our brain and perhaps another hidden one, or even a single brain folding back on itself. Imagine two colossal, flat universes approaching each other across a hidden, extra dimension. When they finally meet, the impact is cataclysmic, releasing an unfathomable amount of energy. This immense energy release is precisely what could generate the incredibly hot, dense conditions we associate with the Big Bang. Instead of a universe spontaneously appearing from a singularity, this collision provides the initial jolt, effectively reheating the universe and setting the stage for everything that follows. It's a universe born not from a point but from a cosmic smash-up. Now, how does this grand collision relate to the formation of the universe's first atoms? The key lies in the sheer amount of energy released during such an event. When these brains collide, this energy is instantaneously converted into a torrent of fundamental particles and antiparticles. Picture a universe filled with an almost perfectly symmetrical blend of matter and antimatter, quarks and antiquarks, electrons and positrons, and so on. In the immediate aftermath of the brain collision, these particles and antiparticles would be created in nearly equal numbers, constantly annihilating each other in flashes of pure energy, only to be created again from the searing heat. It's an incredibly dynamic and chaotic environment, a perfect cosmic dance of creation and destruction. However, for a universe like ours, which is overwhelmingly composed of matter, you and I are made of matter, not antimatter. There must have been a slight asymmetry, an imbalance that favored matter over antimatter. This is where the concept of baryogenesis comes into play, and brain collision models offer compelling avenues for it. During the intense conditions of the collision and the subsequent expansion and cooling, a tiny fraction more matter particles than antimatter particles would have survived the annihilation process. This slight excess, perhaps one extra matter particle for every billion particle-antiparticle pairs, is the key. While the vast majority of matter and antimatter would have annihilated, releasing immense energy, this infinitesimal surplus of matter is what ultimately survived to form everything we see around us. This small asymmetry, generated by the specific physics of the brain collision and the ensuing cooling, is critical. Without it, the universe would be filled only with radiation, with no protons, neutrons, or electrons left over to form atoms. So, the matter that eventually coalesced into the first atoms, the protons and neutrons that would fuse into hydrogen and helium, are the direct descendants of this slight cosmic imbalance. They are the leftovers from a primordial particle-antiparticle war, born from the energy of the brain collision. The ekpyrotic model elegantly explains how such enormous energy could be funneled into particle creation, and also provides a framework for how the necessary matter-antimatter asymmetry could have arisen in that very energetic, violent initial phase. It suggests that the very first atoms are not merely products of an expanding singularity, but rather the durable remnants of a cosmic impact, a thunderous echo from a collision in a dimension far beyond our own, leaving behind the precise building blocks needed for a matter-dominated universe to emerge and eventually sculpt stars and galaxies. Our exploration has taken us through vast cosmic collisions and the hidden architecture of extra dimensions, but now we plunge into a concept that remains firmly in the realm of theoretical physics, yet offers a uniquely mind-bending possibility for how the universe's first atoms came to be. We're going to discuss the incredibly speculative yet utterly fascinating idea of wormholes as early universe conductors. Imagine space-time not as a flat, unchanging stage, but as something that could be warped and folded on itself, creating shortcuts, tunnels, through the very fabric of reality. These are wormholes, theoretical bridges connecting two different points in spacetime, potentially allowing instant travel across vast distances, or even between different universes or different points in time. While macroscopic, traversable wormholes are still the stuff of science fiction, this theory posits that transient, microscopic wormholes might have naturally arisen in the chaotic, quantum-dominated conditions of the extremely early universe, and that their fleeting existence could have profoundly influenced the distribution and creation of our first atoms. In the first moments after the Big Bang, when the universe was incredibly hot, dense, and governed by quantum gravity, space-time itself would have been undergoing extreme fluctuations, as we discussed earlier with quantum foam. Within this turbulent, seething environment, it's conceivable that tiny, ephemeral wormholes could have spontaneously popped into and out of existence. These wouldn't be stable, long-lived cosmic tunnels. Rather, they would be incredibly short-lived, microscopic conduits that lasted for mere fractions of a second. But even in their fleeting existence, they could have acted like cosmic pipelines, momentarily connecting disparate regions of the early universe. Think of it like a sponge, where tiny pores and channels temporarily open and close, allowing fluid to move from one part to another through a shortcut, rather than having to travel along the surface. How could these ephemeral wormholes have influenced atom formation? The key lies in their potential to act as conductors or hotspots of energy and matter. Imagine two scenarios. First, a wormhole connecting two different regions within our own early universe. If one region was momentarily denser or hotter than another, a wormhole could funnel energy or particles from the high-density region to a lower-density one, creating localized enhancements. These sudden, concentrated bursts of energy or matter in specific areas would effectively create pressure cookers, transient regions of extreme temperature and density where the conditions for nuclear fusion, the process that forms hydrogen and helium, could have been dramatically accelerated. It's like having tiny, super-efficient cosmic furnaces appearing randomly, concentrating the raw ingredients for atoms and speeding up their formation. These localized hotspots might have led to slightly different abundances of light elements in specific areas, creating subtle inhomogeneities in the early cosmic soup that could have served as seeds for later structure formation. Secondly, and even more speculatively, what if these primordial wormholes connected our nascent universe to other regions of a larger multiverse, or even to a parent universe that existed before our own? This is where the idea truly becomes wild. A wormhole could hypothetically funnel exotic forms of energy, specific particles, or even the remnants of matter from completely different cosmic domains into our own. This influx could have served as an unexpected source of protons and neutrons, or even pre-formed light elements, bypassing some of the standard nucleosynthesis processes. It's almost as if our universe received a starter pack of atomic ingredients through these inter-universal shortcuts. While highly theoretical, this concept elegantly addresses the question of initial conditions, suggesting that the precise amounts of hydrogen and helium we observe might not be solely a product of our Big Bang, but also influenced by an unseen cosmic exchange. These wormholes, if they existed, wouldn't just be curiosities. They would have been active, albeit temporary, agents in seeding the universe with its most fundamental building blocks, creating local pockets of accelerated atomic creation, almost like cosmic shortcuts for matter, delivering the precise ingredients needed for the universe to begin its grand atomic assembly. While wormholes offer pathways through spacetime, our next theory brings us back to a more familiar, yet still incredibly energetic phenomenon: cosmic rays. These high-energy particles constantly bombard Earth, originating from supernova, black holes, and other violent cosmic events. But what if their early universe counterparts, far more energetic and abundant, played a direct role in shaping the atomic landscape even before stars began their nuclear alchemy? This brings us to a fascinating concept: cosmic rays and early universe chemistry. Typically, we think of cosmic rays as influencing later stellar and galactic processes, but could their primordial predecessors have subtly, or even profoundly, nudged the early cosmic soup towards atom formation in ways not solely reliant on thermal equilibrium? To understand this, we need to consider the extreme conditions of the universe just moments after the Big Bang, a time when the cosmos was a superheated plasma. In such an environment, the concept of cosmic rays might seem out of place. After all, the universe was uniformly hot, and particles were zipping around at incredible speeds due to thermal energy. However, even within this thermal equilibrium, there could have been non-thermal processes at play. Imagine a scenario where certain exotic, highly energetic events within the very early universe, perhaps related to the decay of super-heavy particles from inflation, or mini black hole evaporation, or even phase transitions in fundamental forces, could have generated a population of particles with energies far exceeding the average thermal energy of the rest of the plasma. These would be the primordial cosmic rays, individual protons, electrons, or other fundamental particles accelerated to relativistic speeds carrying immense kinetic energy. Now picture these early cosmic rays hurtling through the hot, dense primordial soup. When such a high-energy particle collides with another particle, the impact can be incredibly violent, far more energetic than a typical thermal collision. These collisions could have provided the necessary energy to overcome activation barriers for nuclear reactions that wouldn't have otherwise occurred at the ambient temperature of the early universe. While Big Bang nucleosynthesis relies on the universe cooling to specific temperatures for hydrogen and helium to form through thermal fusion, these non-thermal, high-energy collisions could have initiated parallel, more aggressive pathways. For example, some models suggest that these extreme particle energies could have driven the formation of rare isotopes, or even trace amounts of elements slightly heavier than helium, by forcing particles to interact in ways not typical for a universally cooling plasma. It's like having a localized particle accelerator randomly appear in the early universe, initiating unique nuclear reactions that wouldn't otherwise happen. Furthermore, these primordial cosmic rays could have influenced the ionization state of the early universe. As the universe expanded and cooled about 380,000 years after the Big Bang, electrons and protons finally combined to form neutral hydrogen atoms, a period known as recombination. This was a crucial step because it allowed light to travel freely, giving us the cosmic microwave background. However, if there were active, high-energy cosmic rays still present, their interactions could have reionized some of the newly formed neutral hydrogen atoms or kept regions of the universe ionized for longer than expected. This extended ionization period could have subtly influenced the processes of atomic formation and the subsequent clumping of matter. It implies a dynamic interplay where the average temperature and density were driving nucleosynthesis, but pockets of high-energy particles were creating localized, non-standard chemical environments. The very energy spectrum and abundance of these early cosmic rays would then directly correlate with the precise abundances of the universe's first elements, adding another layer of complexity to the cosmic recipe. This theory suggests that the universe's first atoms were not just a uniform soup, but a dynamic, energetic tapestry woven by both the gentle cooling of the cosmos and the violent, high-energy impacts of its earliest and most powerful particles. While cosmic rays hint at energetic influences, our next theory takes us into a realm of quantum mechanics so strange and beautiful that it redefines our understanding of what matter itself can be. This brings us to a truly mind-bending concept, the Bose-Einstein condensate universe. Imagine a universe not as a hot, chaotic soup of individual particles, but as a single, macroscopic quantum entity, a superfluid state where particles lose their individual identities and behave as one coherent wave. This isn't just theoretical musing. Bose-Einstein condensates are real, having been created in laboratories on Earth, albeit at incredibly low temperatures, just fractions of a degree above absolute zero. The radical idea here is that perhaps the early universe, in its very first moments, existed in such a state, and the emergence of the first distinct particles, and subsequently, the first atoms, was the result of this condensate, breaking or undergoing a phase transition. To grasp this, let's briefly touch upon what a Bose-Einstein condensate, or BEC, actually is. When certain types of particles called bosons are cooled to extremely low temperatures, they stop behaving as individual entities. Instead, their wave functions, which describe their quantum state, overlap and merge. They fall into the lowest possible energy state, effectively becoming a single, collective superatom. This superfluid possesses bizarre properties like flowing without friction and exhibiting quantum phenomena on a macroscopic scale. Now translate this to the early universe. The theory posits that the universe's initial state wasn't the hot, dense plasma we usually imagine, but perhaps a supercooled, coherent Bose-Einstein condensate of all matter and energy. This doesn't mean the universe was cold in the conventional sense, but rather that its energy was so universally distributed and ordered that it functioned as a single quantum wave. As the universe began to expand, its density would have decreased, and the conditions necessary to maintain this superfluid state would have eventually broken down. This is the crucial phase transition part of the theory. Imagine a giant cosmic Bose-Einstein condensate. As it expands, the individual quantum fields or particles within it would eventually find themselves with enough room and energy to separate and localize. It's like a perfectly ordered crystal suddenly melting into a liquid or a gas condensing into distinct droplets. In this cosmic analogy, the droplets or individual particles that emerged from the breaking condensate would be the fundamental particles we know, quarks, leptons, and the force carriers. These particles wouldn't have been created from scratch. Rather, they would have emerged from an underlying, unified quantum state, much like individual waves appearing from a single, vast ocean swell when it disperses. The implications for the formation of the universe's first atoms are profound. If the initial universe was a Bose-Einstein condensate, then the very distinctness and properties of the first particles, their mass, charge, and spin, would be a direct consequence of how this condensate broke apart. The various excitations or quanta that emerged from the breaking of the BEC would correspond to different particle types. The process wouldn't be about sudden, violent creation from a singularity, but a more graceful, quantum mechanical unraveling of an initial unified state. The stability of protons and neutrons and their ability to bind into hydrogen and helium would then be seen as properties inherent to the way the universal condensate fragmented. The specific values of fundamental constants which dictate particle properties and interactions might even be a consequence of the universal BEC's initial quantum state and the manner in which it decayed. This offers a unique quantum mechanical perspective. The discrete nature of matter, the very solidness and individuality of the particles that form atoms, isn't a fundamental given, but rather an emergent property arising from an early universe that was once a seamless, unified quantum whole. The first atoms, in this view, are essentially the pieces that resulted when the universe's original, singular quantum wave finally chose to manifest itself in discrete forms. While the Bose-Einstein condensate hints at a universe where particles emerge from a unified quantum state, our next theory takes an even more radical stance. It suggests that one of the most fundamental forces in our universe, the very force that pulls apples to the ground and holds galaxies together, might not have been fundamental from the very beginning. This brings us to a truly revolutionary idea: gravity as an emergent force. Imagine for a moment that gravity, the force we perceive as always present and all-pervasive, wasn't initially a standalone, innate property of matter, but rather arose from the complex interactions of other particles and energy in the early universe. This concept is a profound departure from our standard understanding, where gravity is one of the four fundamental forces simply there from the start. To grasp this, consider an analogy from everyday life: temperature. Temperature isn't an inherent property of a single molecule. It emerges from the collective motion and vibration of billions of molecules in a system. Similarly, emergent gravity theories propose that gravity, especially in the extreme conditions of the early universe, might have arisen from the collective behavior of countless microscopic degrees of freedom, perhaps related to the information content within spacetime itself, or the statistical mechanics of underlying quantum bits that make up reality. It's akin to how thermodynamics, which describes heat and temperature, emerges from the underlying, more fundamental laws of quantum mechanics and statistical physics applied to individual particles. In this view, gravity isn't a direct push or pull from a fundamental graviton particle from the outset, but rather a macroscopic phenomenon that reveals itself as spacetime and matter begin to organize. Now, let's consider the profound implications for the formation of the universe's first atoms. If gravity wasn't a fully formed, fundamental force in the very first instance after the Big Bang, but rather emerged slightly later, this changes the entire narrative of cosmic evolution. In standard Big Bang nucleosynthesis, gravity is assumed to be present and active, playing its role in the overall expansion and cooling of the universe. However, if gravity emerged, its appearance could have coincided with, or even directly led to, the precise conditions necessary for atomic structures to coalesce. Imagine a universe where, for a fleeting moment, other forces dominated without the full influence of gravity pulling everything together. Perhaps this allowed for a different distribution of energy or a different texture to the early plasma. The emergence of gravity could then be seen as a phase transition, much like water freezing into ice. As the universe expanded and cooled, and as particles began to interact in more complex ways, the collective behavior of these particles, or the ordering of spacetime information, could have crystallized into the force we recognize as gravity. This emergence would have then rapidly begun to pull matter together, creating the localized regions of density needed for protons and neutrons to find each other and fuse. It's almost as if the universe first needed to form its fundamental particles, and then, from their collective presence and interactions, the force that would bind them together into larger structures like atoms and eventually galaxies simply popped into existence. The timing of this gravitational emergence would be absolutely critical. Too early, and it might have suppressed the initial expansion needed for particle formation. Too late, and matter might have dispersed too widely to ever come together. This theory suggests an intricate dance. Matter and energy first define the conditions for gravity to emerge, and then gravity, in turn, begins to sculpt and organize that very matter and energy. The initial binding of quarks into protons and neutrons, and then protons and neutrons into hydrogen and helium, would thus be intricately linked to the very genesis of gravity itself. The force that would eventually hold the entire cosmic web together might have been born from the very same particle dynamics that led to the formation of the universe's first atoms. It adds an incredible layer of interconnectedness to the cosmic story, implying that the fundamental forces themselves are not static, but dynamic outcomes of the universe's earliest, most extreme conditions, providing the crucial cohesive pull that allowed the chaotic primordial soup to settle into the stable, atomic building blocks of the cosmos. While emergent gravity suggests a dynamic origin for forces, our next theory challenges the very notion of a linear timeline, pushing us to reconsider what beginning even means. This brings us to one of the most profound and mind-bending ideas in cosmology, championed by the late Stephen Hawking, the no-boundary proposal and instantaneous atoms. Imagine a universe where the concept of a singular start or an abrupt end simply doesn't apply to spacetime itself. Instead of a point in time where everything began, picture a universe that, in a sense, has always existed in a unified, timeless state. This isn't about an infinite past in terms of linear time, but rather a different mathematical description of the universe's earliest moments where the very concept of time dissolves. To grasp this radical idea, it helps to think of the universe's origin not as a sharp point, but as the South Pole on Earth. When you're at the South Pole, there's no south direction. Every direction is north. Similarly, the no-boundary proposal suggests that if you trace the universe backward in time, you don't reach a point of infinite density and temperature, a singularity, where the laws of physics break down. Instead, the universe smoothly transitions into a state where time, as we understand it, ceases to have meaning. It's a universe without an edge or a boundary in spacetime. This mathematical elegance avoids the messy problem of what came before the Big Bang, because in this model there simply isn't a before in the temporal sense. Time itself emerges from this timeless state. Now, how does this profoundly affect our understanding of the universe's first atoms? In this framework, the first atoms wouldn't have formed in a linear causal sense as a result of a specific process occurring at a specific time, like Big Bang Nucleosynthesis. Instead, their existence would be inherent to the fundamental nature of the universe itself. If the universe has no temporal boundary, if it is a self-contained, timeless reality, then the conditions that allow for stable atomic structures, the precise values of fundamental constants, the initial distribution of matter and energy, the very fabric of spacetime, are effectively baked into its existence. It's not a step-by-step creation, it's more like a preordained truth of the cosmic whole. This means that the atoms didn't pop into existence at a particular moment, they simply are as part of this unified, timeless cosmos. The implications are truly staggering. If the universe, including its atomic composition, is instantaneous in this non-temporal sense, then causality, as we typically understand it, becomes far less straightforward. We, as observers, experience time linearly, perceiving the universe's evolution from a beginning to an end. But from a God's eye view, outside of spacetime, the entire history of the universe, including the formation of its first particles, might be seen as a single, unified entity. The universe's fundamental properties, its ability to support stable matter, are not the result of a process that happened in time, but attributes of its foundational state. The hydrogen and helium atoms that permeate the cosmos, and which are crucial for forming stars and galaxies, don't arise from a series of sequential events. They are simply intrinsic components of this self-contained, timeless reality. This perspective doesn't offer a mechanism for atom formation in the traditional sense, but rather a profound redefinition of their origin. They exist because the universe, in its very essence, is the kind of universe that contains them. It's a universe where the ultimate question isn't how atoms came to be, but why the universe itself possesses these inherent properties that allow for such atomic existence, transcending the conventional boundaries of time and causality. While the no-boundary proposal suggests a universe without a temporal beginning, our next theory takes that abstract leap even further, proposing that the very fabric of reality isn't just made of matter and energy, but fundamentally of information. This brings us to a cutting-edge and deeply philosophical idea: information theory and atomic genesis. Imagine for a moment that the universe isn't a collection of particles governed by laws, but rather a colossal, self-organizing computational system, where every particle, every interaction, and every structure, including the first atoms, is a manifestation of information processing. This means that the universe computes itself into existence, and atoms are the basic informational bits, organizing themselves into higher, more complex structures. To truly grasp this, we need to shift our perspective on what information means. It's not just data on a computer chip or words on a page. In this context, information is seen as a foundational component of reality, just as fundamental as space, time, matter, or energy. Every single particle has properties mass, charge, spin, and these properties can be thought of as bits of information. The way particles interact, their quantum states, the precise values of fundamental constants, all of this can be described as information. From this viewpoint, the universe is not just described by information, it is information. It's like saying that the universe is a giant, incredibly intricate algorithm running itself, and the output of that algorithm is the physical reality we observe. So, how does this radical concept apply to the formation of the universe's first atoms? Imagine the early universe as a state of incredibly high entropy, a cosmic noise filled with undifferentiated information. As the universe expanded and cooled, it began to process this information, organizing it into more stable, coherent patterns. The formation of the first elementary particles, quarks, leptons, and their antiparticles, can be seen as the initial stages of this cosmic computation, where raw energetic information began to define itself into discrete units. Then, the pivotal moment of quark-gluon plasma condensation, where quarks bound into protons and neutrons, becomes an even more significant informational event. It's the universe reducing its informational noise by creating stable, low-entropy structures. These protons and neutrons are like perfectly encoded informational packets containing precise data about their mass, charge, and spin. The subsequent process of Big Bang Nucleosynthesis, where protons and neutrons fuse to form hydrogen and helium, represents a further step in this cosmic information processing. The universe, through its fundamental laws, which are themselves expressions of information, computed the most energetically favorable and stable configurations of these elementary particles. The formation of a hydrogen atom with its single proton and electron is a perfect example of a minimal, stable informational unit. It's the simplest possible organization of fundamental bits into a coherent structure. The formation of helium, with its specific arrangement of 2 protons and 2 neutrons in the nucleus, represents a slightly more complex yet equally stable informational module. The laws of physics in this view are essentially the rules of the cosmic computation, guiding the self-organization of information into these distinct, identifiable atomic structures. This theory suggests that the universe's inherent drive towards complexity and its ability to harbor life isn't just a physical process, but a direct consequence of its fundamental informational nature. The fine-tuning of fundamental constants, which allows for stable atoms, could be seen as the universe tuning its own parameters to allow for optimal information processing and storage. The stability and distinctness of atoms, their ability to combine into molecules and form complex structures, is perhaps the ultimate manifestation of information organizing itself into physical reality. It's almost as if the universe is an incredibly efficient data center, constantly processing and optimizing its own code, with the first atoms being the initial, essential lines of that code, the stable, foundational bits that allow for the vast, intricate tapestry of cosmic information that is our universe to unfold. While information theory suggests a universe that computes its way into existence, our next theory takes a radically different view, proposing that the universe's birth was far less elegant and orderly. Forget the smooth expansion and uniform cooling. Prepare for a cosmic event that sounds more like a chaotic explosion. This brings us to a highly unconventional yet deeply thought-provoking idea, the Big Splatter theory. Instead of an even, homogeneous expansion from a single point, imagine the early universe as a tumultuous, highly fragmented inferno, where immense, dense clumps of matter splattered into existence across a non-uniform landscape, immediately forming localized regions ripe for atom formation. It's a universe born not with a gentle unfurling, but with a violent cosmic burst creating pockets of intense activity. To visualize this, abandon the classic balloon analogy for the expanding universe. Instead, picture a massive cosmic cannon firing off countless super-dense projectiles into nothingness. Each projectile isn't just matter, it's a concentration of extreme energy and density. From this perspective, the Big Bang wasn't a universal smooth outward flow, but a sudden, highly aggressive creation of enormous inhomogeneities. These splattered clumps would have possessed incredibly high local densities and temperatures, vastly exceeding the average conditions of the surrounding nascent cosmos. Think of it like a cosmic shotgun blast, scattering dense pockets of primordial material in all directions. Because of their immense localized density and heat, these splatter regions would have provided ideal, self-contained environments for rapid, localized nucleosynthesis. The conditions within these fragments would have been so extreme that protons and neutrons fused into hydrogen and helium almost instantaneously upon their formation, even while the rest of the universe was still relatively diffused. The profound implication of the Big Splatter theory is its potential to explain some of cosmology's enduring puzzles, particularly the perplexing existence of seemingly too old galaxies or globular clusters. Standard cosmological models struggle to explain how some massive structures, like early galaxies, appear to have formed so quickly after the Big Bang, seemingly defying the time constraints of cosmic evolution. If the universe started with a splatter, these dense, pre-formed clumps would have acted as immediate gravitational seeds, already packed with the necessary hydrogen and helium atoms. They wouldn't need to slowly accrete matter over millions of years. They would have essentially formed as ready-made galactic cores. This rapid, localized atomic formation within the splattered fragments would accelerate the entire process of cosmic structure formation, allowing for the rapid emergence of massive stellar populations and even proto-galaxies far earlier than traditional models predict. This means the very first atoms in these splattered regions would have participated in an incredibly accelerated form of Big Bang nucleosynthesis, becoming the building blocks of stars and galaxies almost as soon as the universe began. Furthermore, this theory suggests that the universe isn't uniformly homogeneous on the largest scales, but could retain imprints of this chaotic birth. The distribution of matter, the clustering of early galaxies, and even subtle variations in the cosmic microwave background could potentially carry the signature of this non-uniform Big Bang. Instead of a smooth cosmic web emerging from tiny quantum fluctuations, the Big Splatter proposes that the universe's large-scale structure was essentially preceded by these initial high-density fragments. The atoms within these splattered regions would therefore represent the universe's earliest first responders, forming in extreme conditions and immediately embarking on the journey of building the cosmos's most ancient structures. This theory challenges our preconceptions about cosmic elegance, suggesting that the beauty of our universe might have emerged from a primordial chaos, where atoms were forged in the fiery heart of a cosmic impact, leading to a universe that was gravitationally active and structurally complex from its very inception. While the Big Splatter suggests a universe born of chaotic violence, our next theory takes us into a realm where the very nature of matter is challenged, proposing a hidden opponent in the cosmic drama. What if our universe didn't just emerge with a slight imbalance of matter, but began with perfectly equal amounts of matter and its elusive twin, antimatter? And what if a bizarre, hypothetical substance, unlike anything we've ever encountered, played a crucial role in separating them, leaving behind the precise surplus of matter that allowed our first atoms to form? This brings us to a truly mind-bending concept: negative mass and antimatter universes. To understand this, let's first clarify antimatter. For every particle of ordinary matter, like an electron or a proton, there exists a corresponding antiparticle, a positron or an antiproton, with the same mass but opposite charge and other quantum properties. When a particle and its antiparticle meet, they annihilate each other in a burst of pure energy. The puzzle for cosmologists is that the Big Bang, according to our best theories, should have produced equal amounts of matter and antimatter. Yet our universe is overwhelmingly made of matter. If matter and antimatter were truly symmetrical, they would have entirely annihilated each other, leaving behind a universe filled with nothing but radiation. So, where did all the antimatter go, and how did we end up with enough matter to form stars, galaxies, and ourselves? This is where the theoretical concept of negative mass enters the picture, pushing the boundaries of physics into extremely speculative territory. Imagine a substance that possesses mass, but when you apply a force to it, instead of accelerating in the direction of the force, it accelerates in the opposite direction. Even stranger, a positive mass object would be repelled by a negative mass object, while two negative mass objects would attract each other. It's a truly counterintuitive idea, challenging our most basic understanding of gravity and inertia. While there's no observational evidence for negative mass, it's consistent with some mathematical solutions in general relativity. If such an exotic form of matter existed in the early universe, its unique gravitational properties could have provided a mechanism to solve the matter-antimatter asymmetry problem. One intriguing hypothesis suggests that in the very early universe, perhaps immediately after the Big Bang, or even as a consequence of inflation, both ordinary matter and antimatter were created in equal quantities. Simultaneously, or perhaps intertwined with their creation, negative mass particles also came into being. The crucial interaction here is that negative mass would gravitationally repel both ordinary matter and antimatter. Picture a cosmic game of billiards, but with incredibly strange rules. As the universe expanded, the negative mass particles, due to their repulsive gravitational effect, could have acted like cosmic shepherds, actively pushing matter and antimatter apart. They would effectively create gravitational walls or valleys that cleanly separated regions of matter from regions of antimatter. This active segregation would prevent matter and antimatter from annihilating each other on a universal scale. In this scenario, rather than a tiny asymmetry in the production of matter over antimatter, you would have vast, distinct regions of space dominated by one or the other. Our observable universe, then, would simply be the local matter universe that was gravitationally separated from its antimatter counterpart by the repulsive influence of negative mass. The first atoms, hydrogen and helium, would then form within these segregated matter-dominated regions through the standard Big Bang nucleosynthesis processes, now with plenty of raw material to work with. The antimatter, similarly, would form antihydrogen and antihelium atoms in its own isolated domains. These antimatter universes, being pushed away by negative mass, would be effectively unobservable from our matter-dominated region, forever beyond our cosmic horizon. This theory doesn't change how hydrogen and helium formed from protons and neutrons, but it profoundly changes why they could form at all by providing a radical solution to the missing antimatter puzzle. The implications are breathtaking. It transforms the question of atomic origins from a singular event into a grand cosmic segregation, orchestrated by a highly theoretical but mathematically possible form of matter. It suggests that the matter that makes up our bodies and stars isn't just the accidental survivor of a cosmic annihilation, but rather a direct consequence of a fundamental repulsive force that acted as an atomic architect, ensuring enough protons and neutrons were kept safe from their annihilating twins to build a universe teeming with stars and galaxies. It's a universe that started with perfect symmetry, only to have that symmetry broken by the bizarre properties of negative mass, leading to two distinct, unobservable halves of a larger, grander creation, each capable of forming its own atoms but forever separated. While negative mass suggests a cosmic segregation, Our next theory plunges us into the heart of quantum mechanics, proposing that the universe's first atoms weren't just the product of local interactions, but rather emerged from a fundamental, non-local interconnectedness pervasive throughout the cosmos. This brings us to a truly profound and almost mystical concept: quantum entanglement and universal cohesion. Imagine for a moment that every single particle in the early universe, from the fleeting quarks to the stable electrons, wasn't an isolated entity, but deeply, intrinsically linked to every other particle through an invisible, instantaneous bond. This isn't just about particles influencing their neighbors. It's about a fundamental cohesion woven into the very fabric of reality, actively facilitating the self-assembly of particles into atoms, even before the more familiar strong nuclear forces fully asserted their dominance. To understand this, let's briefly recall what quantum entanglement means. When two or more particles become entangled, they share the same fate, no matter how far apart they are. Measure a property of one, and you instantly know the corresponding property of the other, as if connected by an invisible thread, even if they are light years away. This spooky action at a distance, as Einstein famously called it, is one of the most baffling and counterintuitive aspects of quantum mechanics, yet it has been repeatedly verified in countless experiments. Now extrapolate this concept to the entire universe, particularly to its earliest moments, when everything was incredibly compressed and interconnected. The theory posits that the Big Bang didn't just create a multitude of individual particles. It created a universe where every particle was entangled with many others, perhaps even all others, forming a single, coherent quantum state. If such a universal entanglement permeated the early cosmos, its implications for atom formation would be revolutionary. Instead of particles randomly colliding and binding based solely on local forces and thermal energy, the process could have been subtly, yet profoundly, guided by this pre-established quantum harmony. Imagine that the very act of a proton attempting to capture an electron, or of protons and neutrons attempting to fuse, was influenced by an overarching cosmic entanglement. This non-local connection could have created a fundamental attraction or preference for particles to coalesce into stable configurations like hydrogen and helium. It's almost as if the universe had an inherent blueprint encoded in its quantum interconnectedness, pushing it towards atomic organization. For example, the entanglement could have subtly biased the quantum probabilities of certain interactions, making it more likely for particles to find themselves in the right configuration to form a stable nucleus or to capture an electron. This isn't a force in the traditional sense, but a kind of preordained predisposition, a fundamental quantum bias towards cohesion. Furthermore, this universal entanglement might have played a role in stabilizing nascent atomic structures against the incredible thermal chaos of the early universe. In a highly energetic environment where particles are constantly being ripped apart, the quantum bond of entanglement could have provided an underlying stability, making it slightly easier for protons, neutrons, and electrons to remain bound together as they cooled. It's like having an invisible, reinforcing glue that supports the formation of atoms even before the strong and electromagnetic forces become overwhelmingly dominant. This implies a pre-established harmony in the universe's fundamental building blocks, suggesting that atoms weren't just the result of a lucky combination of localized forces and initial conditions, but rather the manifestation of a deeper, cosmic-scale quantum unity. The formation of the universe's first hydrogen and helium atoms, in this view, wasn't merely a product of random chance and local interactions. It was a cosmic ballet of quantum entanglement, where the very act of forming a stable atom was driven by an inherent, non-local quantum predisposition towards universal order and cohesion. While quantum entanglement points to an inherent interconnectedness, our next theory takes that notion of cosmic flow and scales it up to unimaginable proportions, proposing that the universe isn't a one-off event, but part of a grand, eternal rhythm of existence. This brings us to a profound and almost mystical concept, the cosmic cycle of creation and destruction. Imagine the universe not as a story with a single beginning and end, but as an endlessly repeating epic, a cosmic dance where universes are born, evolve, and then eventually perish, only to give rise to new ones. This isn't just about a bounce, as we discussed earlier. It's about distinct, well-defined cycles, each with the potential for its own unique physical laws and initial conditions, subtly or even dramatically influencing how atoms form within each iteration. Our current universe, in this view, is merely one iteration in an infinite sequence, perhaps having achieved the perfect conditions for stable atomic structures through a process of cosmic trial and error. In this sweeping narrative, cosmologists propose various mechanisms for these cycles. One popular idea, often found in theories like cyclic cosmology, suggests that the universe expands to a certain point, then begins to contract, eventually collapsing in a big crunch. However, instead of ending in a singularity, the universe bounces back out into a new Big Bang, initiating a fresh cycle of expansion. Other models involve a kind of cosmic rebirth through the decay of vacuum energy, or even the collision of branes in higher dimensions, as we explored previously. Regardless of the specific mechanism, the core idea remains. The universe is a phoenix constantly rising from its own ashes, each time presenting a new cosmic epoch. The profound implication for the universe's first atoms lies in the idea that each of these grand cosmic cycles might not be identical clones of its predecessor. Think of it like an evolving system continually refining its parameters. Perhaps in earlier cycles, the fundamental constants, the strength of electromagnetism, the mass of the electron, the nuclear forces were slightly different. These variations would have had a monumental impact on the conditions for nucleosynthesis. In some cycles, for example, the strong nuclear force might have been too weak to form stable helium, leading to a universe primarily of hydrogen. In others, perhaps it was too strong, burning through hydrogen too quickly. The possibilities are endless. Over countless eons and innumerable cycles, the universe, through a kind of cosmic evolutionary process, might have discovered or settled upon the precise set of physical laws and initial conditions that are optimally conducive to the formation of stable, diverse atomic structures. Our current universe, then, with its abundance of hydrogen and helium perfectly suited for star formation, and its fine-tuned constants allowing for the creation of heavier elements within stars, could be seen as a particularly successful iteration. It's a universe where the atomic recipe finally hit the sweet spot. This means that the formation of the universe's first atoms, the protons, neutrons, hydrogen, and helium, isn't just a blind accident of our particular Big Bang. Instead, it's the culmination of an iterative process, potentially spanning an infinite number of previous cosmic epochs, each one subtly adjusting the parameters until a stable, life-supporting atomic framework emerged. The atoms that make up our bodies, the stars, and the galaxies around us are not just recent creations. They are the beneficiaries of an immeasurable cosmic heritage, the perfected blueprint refined over eons of universal births and deaths. This cosmic recycling implies a deep, ongoing process of self-optimization within the universe, constantly experimenting with its own fundamental laws until it achieves a state perfectly poised for complexity to arise, ensuring that the critical building blocks for everything, the stable first atoms, are constantly renewed and finely tuned for the next grand iteration of the cosmos. While the cosmic cycle theory paints an epic picture of universal rebirth, our next idea plunges us into the dizzying depths of quantum mechanics, hinting at a connection between consciousness and reality so profound it challenges everything we think we know about the universe's beginning. This brings us to a truly mind-bending, deeply philosophical, and highly speculative concept: observer-created reality and the quantum Zeno effect. Imagine for a moment that the very act of conscious observation isn't just passively receiving information about the universe, but actively participating in its formation. Could the emergence of the universe's first atoms, those fundamental building blocks, have been influenced in some bizarre way by the eventual presence of conscious observers, even if those observers didn't exist until billions of years later? To even begin to grasp this, we need to dip our toes into the strange world of quantum mechanics, the set of rules governing the incredibly tiny. At the quantum level, particles don't exist in a definite state until they are measured or observed. Instead, they exist in a superposition of all possible states simultaneously, like a wave of probabilities. It's only when an observation is made that this wave function collapses and the particle chooses a single, definite state. The famed double-slit experiment perfectly illustrates this. If you don't observe which slit an electron goes through, it behaves like a wave, creating an interference pattern. But if you do observe it, the wave function collapses and it behaves like a particle going through only one slit. This inherent fuzziness of quantum reality, until observed, is central to the concept we're exploring. Now, layer onto this a phenomenon known as the quantum Zeno effect. This effect, named after Zeno's paradox of the arrow, suggests that if you continuously and rapidly observe an unstable quantum system, you can effectively freeze its evolution. The act of repeated measurement prevents the system from decaying or changing its state. It's like constantly poking a quantum particle, preventing it from doing anything else. While this has been demonstrated in laboratory settings with individual particles, applying it to the entire universe, especially its earliest moments, is an enormous conceptual leap. The radical interpretation of observer-created reality, in the context of the quantum Zeno effect, posits that the early universe might have existed in a quantum superposition of countless possibilities. In this initial state, the fundamental particles, quarks, electrons, and the forces that bind them might not have had definite properties. They were waves of probability, existing in a multitude of potential configurations. It was only with the eventual emergence of conscious observers like us, billions of years later, that these probabilities collapsed, fixing the properties of these fundamental particles and their interactions into the stable forms we recognize. This suggests a backward causation where the future act of observation somehow solidifies the past. So, how would this bizarre mechanism apply to the formation of the universe's first atoms? Imagine that the universe, immediately after the Big Bang, was a quantum soup where protons, neutrons, and electrons existed as probabilistic waves. Their ability to form stable hydrogen and helium atoms was merely one of many possibilities. In a universe without observers, perhaps these wave functions would have remained diffuse, never fully materializing into definite atomic structures, or perhaps decaying rapidly. But the eventual existence of conscious beings, looking back at the cosmos, might have acted as the ultimate measurement, forcing those early wave functions to collapse into the stable configurations of hydrogen and helium atoms that we observe today. It's as if the universe, in a quantum sense, was waiting for consciousness to emerge to choose its atomic reality. This is not to say that a conscious being literally reached back in time to assemble atoms. Rather, it implies a deep, fundamental interconnectedness between the observer and the observed, where the very act of awareness plays a role in manifesting physical reality. The stability of the universe's first atoms, their precise properties, and their abundance would not just be the result of physical laws and initial conditions, but somehow intertwined with the universe's inherent capacity to produce observers. While highly controversial and resting on the most radical interpretations of quantum mechanics, this theory blurs the lines between mind and matter, suggesting that the existence of every hydrogen atom, every helium nucleus, might be a profound testament to the universe's journey towards self-awareness, where the earliest building blocks were, in a sense, waiting for an observer to solidify. Their existence, while observer-created reality, delves into the philosophical nature of consciousness. Our final theory brings us back to the realm of physics, albeit at its most speculative and extreme. This idea proposes that our universe isn't a singular entity, but part of an infinitely branching cosmic family, where every quantum possibility spins off into its own unique reality. This brings us to the extraordinarily popular, yet deeply challenging, many worlds interpretation and particle divergence. Forget the idea of a single Big Bang leading to one set of fixed atomic outcomes. Instead, imagine a universe where every single quantum event, every decision made by a subatomic particle, irrevocably splits the universe into countless parallel realities, each representing a different outcome. To grasp this, let's revisit the concept of quantum superposition we discussed earlier. In standard quantum mechanics, a particle exists in all possible states simultaneously until observed, at which point its wave function collapses into a single outcome. The many worlds interpretation, first proposed by Hugh Everett Roman III, offers a different solution to this collapse problem. It suggests that the wave function never truly collapses. Instead, every time a quantum measurement or interaction occurs, the universe itself branches into a multitude of parallel universes, each representing one of the possible outcomes. If an electron can go through either slit in the double-slit experiment, in the many worlds interpretation, the universe splits. In one universe, the electron goes through slit A. In another, it goes through slit B. All possibilities are realized in their own distinct realities. This isn't a theory about alternate dimensions separated by vast distances. It's about an ever-growing tree of realities, continuously branching with every quantum interaction. Now, imagine the implications of this for the formation of the universe's first atoms, particularly in the incredibly dense, hot, and quantum-dominated environment of the early cosmos. Every single interaction between quarks, gluons, protons, neutrons, and electrons in the primordial soup would have been a quantum event, leading to an incomprehensible number of branching realities. When a proton and a neutron had the possibility of fusing to form deuterium, in one universe they would fuse, creating the first building block of heavier elements. In another, they might bounce apart, remaining as individual particles. Every time a specific nuclear reaction took place or didn't take place, the universe would have diverged into countless new branches, each with a slightly different atomic composition. This means that the universe's first atoms, the hydrogen and helium that dominate our cosmos, aren't just the product of one single, fixed sequence of events. Instead, they are the specific outcome realized in our particular branch of the cosmic tree. In other parallel universes, the conditions, the quantum interactions, or the fundamental constants might have settled or diverged differently. There might be universes where the proton-neutron ratio was slightly off, leading to much less helium. There could be branches where the strong nuclear force led to different stable nuclei, creating a universe with an entirely alien periodic table. Or even universes where stable atoms never truly formed, remaining as a chaotic soup of fundamental particles. Our universe, then, is simply one of the branches where the quantum lottery worked out perfectly for stable hydrogen and helium to form in the precise abundances we observe. The many worlds interpretation applied to early universe nucleosynthesis means that the atoms that make up our bodies, our stars, and our galaxies are not just the product of a singular Big Bang, but rather the manifestation of a uniquely successful sequence of quantum divergences. It suggests that the formation of the universe's first atoms wasn't a predetermined, exclusive event, but one of an infinite array of possibilities that were all actualized in their own separate realities. It paints a picture of a cosmos where atomic creation is not a singular, linear process, but an infinitely diverse, branching phenomenon, making the existence of our specific universal chemistry not just a fact, but a unique realization among countless cosmic alternatives. And with that, we've journeyed through 30 incredible, mind-bending theories about the absolute origins of everything. Our exploration has taken us on an incredible journey through 30 wild, wonderful, and sometimes wonderfully wacky theories about the universe's first atoms. We've ventured into hidden dimensions, witnessed cosmic collisions, and pondered the very nature of reality. Now, as we reach our final theory, we arrive at a concept that for some is the most unsettling of all, precisely because of its austere simplicity. This brings us to Theory 30, the just-so universe. This idea doesn't offer a grand mechanism or a hidden force for the creation of the universe's first atoms. Instead, it posits that they formed simply because the conditions were just so, a unique and profoundly improbable cosmic accident, a lottery win against truly astronomical odds that somehow resulted in stability and complexity emerging from the primordial chaos. To truly appreciate the weight of this just-so notion, we need to reflect on the staggering level of fine-tuning we've touched upon repeatedly throughout this journey. Think about the fundamental constants of physics, the precise strength of the strong nuclear force that binds protons and neutrons, the delicate balance of the electromagnetic force that holds electrons in orbit around nuclei, the exact mass difference between a proton and a neutron, the expansion rate of the universe, and even the initial density fluctuations from the Big Bang. If any of these values were even infinitesimally different, if they were nudged by just a hair's breadth from their observed values, our universe would be radically different, and importantly, atoms as we know them, the very building blocks of stars, planets, and life, might never have formed. For instance, if the strong force were a tiny bit weaker, atomic nuclei beyond hydrogen simply wouldn't hold together. No helium, no carbon, no oxygen. A universe filled with nothing but diffuse hydrogen, incapable of evolving complexity. If it were slightly stronger, hydrogen itself might be unstable, fusing too quickly, burning out the cosmos before it even truly began. The list of such precise calibrations goes on, encompassing dozens of parameters, each one seemingly tuned to an exquisite degree. The just-so universe theory doesn't attempt to explain why these conditions are so perfect. It offers no deeper mechanism, no overarching design, no hidden dimensions influencing our constants, no previous cycles refining the recipe. It simply acknowledges the incredible unlikelihood of our universe's parameters being precisely what they are, without necessarily positing a grander cause beyond pure chance. It suggests that out of an almost infinite number of possible universes, each with its own random set of fundamental laws and constants, we just happen to inhabit the one where the dice rolled perfectly. We hit the cosmic jackpot. It's the ultimate expression of cosmic fortuity, a singular stroke of luck that allowed the raw energy of the Big Bang to coalesce into stable, distinct packets of matter. The formation of the universe's first hydrogen and helium atoms, in this view, wasn't destined or engineered. It was simply the improbable outcome of a random draw from an unimaginably vast cosmic possibility space. This perspective can be deeply unsettling for those who seek a deeper meaning or a logical progression in the universe's origins. It leaves us with a stark, almost brutal recognition of our unique existence. However, it also imbues the existence of those first atoms and everything that followed from them with an extraordinary sense of wonder. To contemplate that the vast, complex cosmos, with its swirling galaxies and vibrant life, all sprang from an unbelievably lucky combination of numbers at its very inception, that the formation of the first atoms was simply a cosmic dice roll gone incredibly right, is to confront the universe on its own terms. It's an improbable yet undeniable reality. It means that the hydrogen in a distant nebula, the helium within our sun, and indeed the atoms that compose our very bodies, are all testaments to a cosmic lottery win of an unimaginable scale, leaving us with not just a sense of cosmic wonder, but perhaps a profound, almost existential awe at the sheer, beautiful improbability of it all. Our cosmic journey has spanned an incredible intellectual landscape, delving into 30 truly mind-bending theories about how the universe's first, most fundamental building blocks, those essential atoms, might have come into existence. We've traversed from the rigorous scientific predictions of Big Bang Nucleosynthesis, which shows us exactly how hydrogen and helium were forged in the universe's early furnace, to the wilder, more speculative realms of primordial black holes acting as tiny cosmic foundries. We even dared to consider the unseen, pondering how mysterious dark matter might have subtly, yet profoundly, influenced the atomic recipe. We ventured beyond the Big Bang itself, exploring concepts like a pre-cosmic foam, a seething quantum sea from which our universe might have emerged, and the mind-boggling notion of a multiverse where countless realities constantly branch, each potentially experimenting with its own unique atomic laws. Our expedition then navigated through the powerful elegance of inflationary field decay, describing how the universe's exponential growth spurt could have birthed all fundamental particles from pure energy. We explored the bizarre relics of topological defects like cosmic strings that might have acted as gravitational scaffolds, concentrating matter for super-efficient atomic creation. We challenged the very notion of fixed laws, contemplating a universe where fundamental constants were dynamic, constantly calibrating the conditions for atomic stability. And we embraced the deepest quantum mysteries, from the idea of the universe as a self-organizing system that inherently trends towards atomic order, to the profound implications of Bose-Einstein condensates, where all matter once existed as a single, coherent quantum entity before breaking into distinct particles. We even asked if gravity itself was an emergent force, solidifying into existence just in time to bind the first atoms. We further pushed the boundaries of our understanding, contemplating the timelessness of the no-boundary proposal, where atoms effectively always were as part of a unified cosmos, and mused about the universe as a grand computational system, where atoms are fundamental bits of information processing themselves. We plunged into the chaos of the Big Splatter theory, envisioning a universe born from violent, fragmented eruptions of matter, and wrestled with the perplexing puzzle of antimatter, solved perhaps by hypothetical negative mass separating matter from its annihilating twin. We even touched upon the profound interconnectedness of quantum entanglement, suggesting a universal cohesion that inherently favored atomic formation, and explored the grand cosmic cycles where universes are endlessly reborn, perhaps refining the atomic recipe with each new iteration. Finally, we grappled with the radical idea of observer-created reality, hinting that consciousness might play a role in solidifying atomic existence, and the dizzying implications of the many worlds interpretation, where every quantum possibility spins off a new atomic reality. And we concluded with the humble yet awe-inspiring "just so" universe, reminding us that the sheer, improbable luck of our cosmic parameters allowed atoms to form against astronomical odds. Each of these theories, whether firmly rooted in observation or soaring on the wings of pure speculation, reminds us that the quest to understand our origins is a journey without end. These are not just abstract scientific concepts, they are profound explorations into the very fabric of reality, pushing the boundaries of what we thought possible and revealing the incredible ingenuity of the cosmic dance that created everything we know. They highlight the breathtaking precision, the immense energy, and the deep mysteries embedded in the universe's earliest moments. The humble hydrogen and helium atoms that formed in those fleeting first minutes were not simply particles. They were the essential cosmic seeds, the ultimate starting point for every star, every planet, and ultimately every living thing, including you and me. So, after this extraordinary ride, what do you think? Which of these 30 theories about the universe's first atoms resonated with you the most, or perhaps blew your mind clean open? Do you have another wild, imaginative idea about how these fundamental building blocks came into being? Share your thoughts and questions in the comments section below. We love hearing from our cosmic curious community. If this deep dive into the unknown sparked your sense of wonder, please give this video a thumbs up, Subscribe to our channel for more expansive explorations into the mysteries of space, and make sure you hit that notification bell so you don't miss our next adventure. Until then, keep looking up, keep asking the big questions, and keep exploring the endless wonders of our incredible universe.